Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here, along with my younger brother, AJ Raj. As you can see today, we're going to be covering an Algebra 2 lesson, and in this Algebra 2 lesson, we're going to be wrapping up the instructional lessons on inverse relations and functions. So this is going to be part 3. In the next 2 videos, we'll be focusing on some practice problems for all of you, but like I said, this video is going to wrap up the instructional or the learning part of inverse relations and functions. So in this video, we're going to look at 2 more practice problems 5 and 6. The first one, practice problem number 5, is going to include a word problem where we're going to find the inverse of a formula we've been given. The formula is going to be about gravity, and the reason that I talk about gravity and I even put this image up here is because it's a great way to implement a formula and then find the inverse of a formula to solve whatever the application is asking. So it's going to be a word problem, a real life application, and it's going to do with gravity and jumping off of a cliff into an ocean. So that's why I put this image up. 2 people are diving off of a cliff into water. So that's what the concept of that word problem is going to be. Afterwards, we're going to look at practice problem number 6, and practice problem number 6 has 3 parts that we're going to be covering. This practice problem is going to be about composing inverse functions. This whole unit is a mishmash of different things, but because this lesson was specifically requested, I didn't get to cover composite functions with all of you, but we're going to talk about how we could implement composite functions into inverse functions and their original functions, see what properties there are, see what happens, and things like that. So we're just going to understand how do we incorporate composite functions into our learnings about inverse functions. So before I get into the video, I'd really appreciate it if you all could like the video, subscribe to our channel, hit the post notification bell, drop a comment down below, and share using all our socials, which you can find in the description box. Alright, so let's get right into the first problem, problem number 5. Just like I was telling you, the word problem about finding the inverse of a formula we've been given regarding a specific real-life situation. So here's the problem. So I'm just going to read the problem out to you. The function d equals 4.9 t squared represents the distance d in meters that an object falls in t seconds due to Earth's gravity. So the function d equals 4.9 t squared is the formula we're going to be working with. D is almost like our y, if you want to think of it, and then t is almost like our x. D represents the distance that an object is going to fall if you drop it from a specific height until it hits the ground, or in this case, a body of water. Whatever just stops that motion, and then t is going to be the amount of seconds it takes for that object to fall from wherever you've thrown it, or if you're the object, wherever you've jumped from. T is going to be the amount of time it takes for you to hit that surface that stops your downward motion due to gravity, because Earth's gravity is constantly pulling objects down towards the Earth's center or the core. So what we need to do with this problem is we need to consider the inverse. We're not exactly finding the inverse, but we need to consider what is the inverse, and then afterwards we have to actually determine how long in seconds does it take for the cliff diver shown to reach the water below. I know the image isn't shown yet, but I will show you an image. You're going to see a cliff diver jumping off of a cliff into water, and then you're going to be given d, which is the distance. So you're already given one of the variables. You're going to be given d, which is the distance that it takes for the cliff diver to jump off the cliff and hit the body of water. And we're finding t, which is the amount of seconds it takes for the cliff diver to jump off and dive into the water. So that's what we're solving for using this formula d equals 4.9 t squared. So here's your solution. Before we even get into the solution, here's the image I was talking about. Here's your cliff diver jumping off a cliff into the water. And you can see there's a measurement given that's 24 meters. So the distance, in this case, d is equal to 24 meters. So knowing this measurement, we just had to figure out what t is. So we need to know how much time it'll take for the cliff diver to hit the water. Here's your solution already pre-written for you. I'm going to go through this again with you, so no worries. Alright, so I'm just going to go through that solution again with you. First, we want to write the formula we've been given. And the formula we've been given is d, which is distance, is equal to 4.9 t squared. T squared is your time in seconds. This represents gravitational pull in this case. And in addition to this, we need to identify what variables we've actually been given. So we can consider these our givens in this problem. In this problem, we have two variables, d, distance, and d, seconds. In this case, we've been given the distance, which is 24 meters. So we need to identify that. So d is equal to 24 meters. So now all we have to do is solve. So if this coefficient, if this term right here, 4.9 t squared, is equal to d, and this constant 24 is equal to d, well, what we can do is we can just set them equal to each other because they're both equal to d, meaning they're both equal to each other. So technically, we could rewrite this as 24 equals 4.9 t squared. And all we have to do is go about solving for t by isolating t. First, what we want to do is we want to divide both sides by 4.9 to get t squared by itself, because remember, when we do PEMDAS, the exponents would come first, but since we're kind of going in the reverse way because we're trying to isolate the variable, we will start with division in this case. So let's divide both sides by 4.9. If you have a calculator out, that's best. We can round our answer to the nearest thousandth, and if you do that correctly, you'll get t squared is approximately equal to 4.898. Now all that's left is square rooting both of the sides. So the square root of t squared is just t, and the square root of 4.898, if you plug that into the calculator, will be 2.213. So 2.213 seconds is your answer. Seconds. So that's your answer. When I say consider the inverse, almost like in this function, d equals 4.9 t squared is your formula. In this application, that's the formula you've been given. So technically, this formula is given because the formula is given assuming that you would know what t or the time is, and you would just plug that into the formula because t is like your x. We typically plug x into the formula. However, in this case, we kind of did the opposite. In this case, we were given y, or d in this case, so we plug whatever value we have for d into the formula, and now we're solving the other way. So instead of being given x and solving for y, we're given y and we're solving for x. So you can consider that like the inverse. So that's why I said consider the inverse. All right, so let's move on to the next slide, actually. Here's a key concept I do want to go over with all of you before we get into practice problem number 6, which is about the composition of inverse functions. So the key concept here is composition of inverse functions. So if we have two functions, if we have function f and we have f inverse, which is denoted by f to the power of -1, again, that's the inverse of the original function. If these are inverse functions, then the following that I'm about to tell you is true. So as long as these two f and f to the power of -1, which is inverse, if these are two inverse functions, then what I'm going to say is true. So look at this notation, take a minute to just look at it and try to understand it, because this has to do with composite functions. So in this case, we have f inverse here. We know this notation. Then we have this circle. So what is this circle right here? Well, this is what we call a composite operator. I hope I spelled that right, operator. So that's a composite operator. And then after the composite operator, we have f, which is our original function. So what this means is that we're looking at a composite function. So this because we have the composite operator here, we can rewrite this, whatever is in the set of parentheses, as f inverse, put the f in the parentheses of x, because don't forget we have x in parentheses over here. So this is another way to write what's given here. The composite operator is just indicating to you that you're working with a composite function. And what is a composite function? Well, a composite function in layman's terms is just a function within another function. So in this case, because f inverse comes first, f inverse is going to be the function on the outside, like I show you here. However, because f comes after the composite operator, f is going to be the function on the inside. As you can see, what I wrote down here, f is on the inside. So what happens is when you have this composite operator, whatever x value you've been given in this first scenario, you're first plugging it into the function f and then getting a value, which is your output. And then after you get that output, you are then plugging it into f inverse. So it's like you're doing two function operations back to back. So what happens in this case is you can see that I wrote this is equal to x. So what does that mean? Well, think about it this way. If I'm taking a number, which is x, and I'm plugging it into f, I'm going to get some kind of output. Then I'm going to take that output and I'm going to plug it into f inverse. So f plugging that first number, which was x, into f does something, and you get some kind of output. However, you can think of f inverse as the opposite, or the reverse. So if I take whatever output came from f of x and I input it in f inverse, it's going to undo what the original function did to our input. So it's going to undo that, and then what it's going to spit back out is the original number you actually input into this composite function. So let's say I input x into this composite function. Let's say I was trying to find f inverse of f of 1. So I would plug 1 in, and I would get whatever f of 1 is equal to, which is the output. Then I would plug the output of f of 1 into f inverse. If I plug that output into f inverse, I should be able to get 1 back, because again, we're just undoing what was done with the first function operation. The same thing applies here. In this case, the positions of f and f inverse have been swapped. F comes first before the composite operator, and then f inverse comes after. So this can be written as f is the function on the outside. Whichever function comes before the composite operator is the one that comes on the outside, and then whatever comes after the composite operator is the one that goes on the inside. So this is pretty much also rewritten as f of f inverse of x. So f inverse is the function on the inside. So if you're given a value x, you would first plug it into f inverse, and then you get the output. Then you would get the output and plug it into f, which is the function on the outside. However, whatever number we plug into f inverse, we're going to get some kind of output. So f inverse has some kind of effect on the input we put in. Then we're going to take that output and plug it into f of x. And when we plug in f, what happens is whatever f inverse did to that original input is going to be undone or reversed. So we're just going to spit back out the original number we input, which was x. So if we use that example of 1 again, if we find f inverse of 1, we're going to get some kind of result or output. If we input that output into f, then we're going to just undo what was originally done, and then the composite function is going to spit 1 back out again. All right, so this is all true as long as x is in the domains of f and f inverse respectively. So as we said before, functions have domains that are continuous, that continue from negative infinity to positive infinity, like we looked at in the last video. These are true functions. However, sometimes you're going to get inverses, or you're going to get your original function or relation that is not going to be a true function, because it's going to have breaks in its domain. It's going to have points of discontinuity, like maybe holes. It might have infinite discontinuities, like asymptotes, just things that cause breaks where the x value does not have a corresponding y value, and therefore that x does not belong in the domain of the function or its inverse. In that case, if the x that you're inputting into the composite function does not belong in the domain of either f of inverse or f, then what's going to happen is this rule does not apply anymore. So the x that you're inputting into your composite function must belong in the domains of f and f inverse. Let's say, for example, in the first example, f inverse of f of x. Well, let's say that f of x has a point of discontinuity at 1, at x equals 1. So if you input 1 into f of x, this property does not hold true. You can't just spit 1 back out after you do both of the functions, after you do the whole composite function operation, because 1 does not even belong in the domain of f. So you're just going to get undefined. So just keep that in mind as we go through these 3 examples. So here's the first problem. Problem number 6a, composing inverse functions. In this problem, we're given the original function f of x equals 1 divided by x minus 1, and we're asked what is each of the following. So in this case, we're trying to find f inverse of x. So we're pretty much trying to find the inverse of the function we've been given. So here's the solution already pre-written for you. I'm going to go through this again with you. It's very simple. We're just finding the inverse of the function we've been given. So we're trying to find f inverse of x, and this is the notation f to the power of negative 1 of x. So I'm going to write the original function we've been given, y equals 1 over x minus 1. Remember, our first step is to swap the x and the y. So in this case, I'm going to rewrite it as x is equal to 1 over y minus 1. So you just swap the positions of the x and the y. Your next step is to just solve for y. So how are we going to solve for y? The first step we're going to do is we're going to try to get y out of the denominator. And how are we going to do that? Well, we can multiply both sides of this equation by y minus 1, which is the denominator. If we do that on the left side, we will end up getting x times y minus 1. And then on the right side, if we multiply 1 over y minus 1 times y minus 1, the y minus 1 in the numerator and the denominator are going to cancel, and then you're just going to be left with 1. And then to get y minus 1 by itself, we can divide both sides by x. So if we do that, we'll get y minus 1 is equal to 1 divided by x, because if we divide 1 by x, x becomes the denominator. And then our last step is to just get rid of this negative 1. So we're going to add 1 to both sides, and we will get y equals 1 over x plus 1. And that is your inverse function. So you can also write this as f inverse of x is equal to 1 over x plus 1. And that's your inverse. So moving on to the next problem, problem 6b, we're going to continue to compose inverse functions with that same original function of f of x equals 1 over x minus 1. Now we have to find the following, which is, well, we're looking at a composite function now because we see the function operator. This is, we're finding f of f inverse of 1. So now let's get to solving that. Here's your solution already pre-written for you. I'm going to walk through this again with you. So let's just rewrite what we've been given with the function operator. So what we're trying to solve is f, then we're going to have the function operator, f inverse of 1. So 1 is going to be our x, our input. And remember from the previous slides I showed you, if f inverse is the inverse of f, which it is, if these are inverse functions, which they are, and 1 belongs in the domain of both of these functions, then if 1 belongs at least first in the domain of f inverse, and whatever the output of f inverse belongs in the domain of f, then our output is just going to be 1. So in this case, we're just checking, does this work if we input 1 into this composite function? Well, I'm just going to rewrite this with the function operator as f of f inverse of 1, because that's just easier for me to understand, easier for you to understand as well, probably. Now what we're going to do is we're going to take 1 and first input it into f inverse. And recall f inverse from the last slide that we found, f inverse is equal to 1 over x plus 1. That's what we found on the last slide. So first we're going to input 1 into f inverse. So I'm going to write this as y. I'm not going to write f inverse. I'm going to write y. So y is equal to, like we said, the inverse was 1 over x plus 1. So in this case, we're just going to plug 1 in for x. And if we do that, we end up getting 1 over 1 plus 1. 1 divided by 1 is 1. So we add that other one we have, and 1 plus 1 is equal to 2. So this is the output we get for f inverse of 1. Now we got to plug this output into f, and we need to see, does 2 belong in the domain of f? If it does, then our output should be equal to, our final output should be equal to 1. So our final answer should be equal to 1. Recall that f of x is equal to 1 over x minus 1. So we're just plugging 2 in for x. So again, I'm going to write this as y. So f of x is y. Y is equal to 1 over x minus 1. Again, we're plugging 2 in for x. So we get 1 over 2 minus 1. 2 minus 1 in the denominator is 1, and 1 divided by 1 is 1. So our final answer is going to be 1. So the property was true, and it worked out. So our final output is going to be equal to 1. Now let's look at our final problem, problem number 6c, again composing inverse functions using the original function f of x equals 1 divided by x minus 1. Now we're looking for the following, which we're pretty much switching the positions of the two functions around the function operator. Instead of doing f inverse first and then f, now we're doing f first and then f inverse. So let's do that now. Here's your solution already pre-written for you. You can see it's a lot different from the last problem, and I'll explain exactly why this occurs. Alright, so let me rewrite the original composite function we've been given. So we're doing f inverse, and then the function operator, and then f. And then we're plugging 1 in. So we're using the same x value or input, but we're just switching the positions of the two inverse functions. So we can rewrite this as f inverse is the function on the outside because it comes before the function operator. F inverse is on the outside, and then f of 1 is going to be on the inside. So this is f inverse of f of 1. All right, so let's go about solving this. Again, I just want to remind you, f of x is equal to 1 over x minus 1, and f inverse is equal to 1 over x plus 1. Yeah, I'm just checking to make sure. Okay, yeah, that's correct. So the first thing we want to do is we want to plug 1 into f. So again, f, we're going to write f of x, we're going to write as y. y is equal to 1 over x minus 1. We're going to plug 1 in for x because that's the input we've been given. So if we plug 1 in for x, we get 1 over 1 minus 1. What happens is you can see 1 minus 1 in the denominator is going to leave you with 1 over 0. And recall, if we have a number divided by 0, this is undefined. It just does not work. You cannot divide a number by 0. If you do that and you plug it in your calculator is going to give you an error. It's okay to divide divide 0 by a number, that's okay. But you cannot divide a number by 0. So in this case, this answer is going to be undefined. It's going to be undefined because it's not a real number. And if it's not a real number, doesn't necessarily mean that it is an imaginary number. It just does not exist. This just does not work. You cannot have a number divided by 0. So for all our purposes, think of it like that. You might be wondering, how come this happened? The last problem was perfectly fine. We were able to use the property we learned. Whatever we input into the inverse function, composite functions, we were able to spit that right back out. Well, think of it this way. Think of the domain of f. So think of the domain of f. Remember, f is 1 divided by x minus 1. So what does this look like? This looks like the functions we were working with in the last unit, the rational functions we were working with. And if you think about it, the domain of f is equal to negative infinity to 1, then there's going to be a union or a break in the domain, and then it's going to continue from 1 to infinity. So this function continues from negative infinity to positive infinity except at the point where x equals 1. And why is that so? Well, take the denominator and set it equal to 0. So x minus 1 is equal to 0. Therefore, there's actually a vertical asymptote at x equals 1. And because there's a vertical asymptote at x equals 1, the input that we're putting in is actually 1. So that actually creates a conflict because you cannot input 1 because you're just going to get 0 in the denominator. So there's a vertical asymptote at x equals 1. There's no value for this function at x equals 1 because there's just a vertical asymptote. There's no point. There's no corresponding y coordinate for this x coordinate. And I want you to keep in mind that whatever we input, whatever x value we're inputting into the first function, and then whatever output we get that we're inputting into the second function in this composite function scenario, it must be in the domain of f. So keep in mind, it must be in the domain of f. That was that last rule we were looking at. It must belong in the domain of f for this to be true. Alright, that's all I have for you today. I hope you enjoyed the lesson and stick around for some more practice problems if you want to prepare for any assessments that you might have in class regarding this topic, inverse relations and functions. I hope you enjoyed the video, and if you did, please like, subscribe to our channel, hit the post notification bell, drop a comment down below, and share using our socials. You can also check out our website for more materials and email us at our Gmail for any questions, inquiries, concerns, anything at all. Thank you for watching and stay tuned for my next video. Bye!